Okay, so we want to find a good characterization of planar graph. When a graph is given, we want to know whether this is a planar graph or not. For that, we consider two graph operation, which are subdivision and minor. We have learned about subdivision before, but let's recall it. We say subdivision of F, or we simply say F subdivision. On F subdivision is a graph which is obtained from a graph F via edge subdivisions. And here, edge become passes to new vertices of degree 2. And if the vertices in F all have degree at least 3, and H is on F subdivision, then the vertices, so say you have this graph and then you consider its subdivision, and these vertices are actually corresponding to these vertices. And these vertices are new vertices, which doesn't correspond to any vertex in the original graph. And we give name to this vertex. And the name is, they are called the branch vertex. And the vertices having degree at least 3 in H are the branch vertices of H. And these are the images of vertices of F. Okay, you can already see that this and this have the essentially same planar embedding, but topologically they are same. This, as the vertices are just point, this image of this edge, which is curved on here, and then this image of this path is curved. So once you draw on the plane, drawing one and drawing the other are same. So this subdivision is a natural operation we consider for studying planar graph. And we say that graph H is a minor of G, or G contains an H minor if H can be obtained from G by deleting adjacent vertices and contracting the matches. Yeah, contraction we have dealt with in the section of connectivity. And when we have G, we delete the matches and vertices, then we obtain a subgraph. And then we further contract some matches as we want. Then we get some other graph, and then that's called H minor if it is H. Okay, and we say that our graph H is a topological minor. Of G, or we say G contains H topological minor. If G contains subdivision of H as a subgraph. So in other words, you delete the vertices, delete the edges, and subdividing some edges to obtain the other way around. Sorry. Delete some vertices, delete some edges, and then you replace passes into edges so that you obtain H. Then you say that the G contains a H topological minor. Again, note that these relations are motivated from plane embedding, as subdivision preserves the planarity. If you have a graph and then you subdivide on H, and if the original graph is planar, then new graph is planar. And also minor relation preserves planarity. So deleting H, deleting vertices, then the original graph is planar, then new graph is planar. Contraction as well, you have a plane embedding, then you just shrink this edge into one vertex, 1 point. And then while you're doing that, you might want to delete this edge. And then depending on whether you decide to keep the multiple edges or not, you might have to delete some edges. So here, again, the basic assumption is that you delete the multiple edges and you delete the loop that arise when you are contracting. So, this just shrink this, and while you're shrinking it, you continuously move your embedding, and then you delete some edges, and that's the resulting graph. So it preserves the planarity. Okay. Fine. So now what do we know? This preserves the planarity means that if you have G, if G contains an H minor or H subdivision, then and G is planar, then H is also planar. So this we know, right? And then previously we find two non-planar graphs, K5 and K33. Using that, what do we get from here? It says that if a graph G contains either K5 minor or K33 minor, then it is not planar. So we know this. Okay. So if you put H here as a K5 or K33, then the conclusion is wrong. This is not planar. you take the contrapositive, then what you get is that G is not planar. So we know this. So having no K5 or K33 as minor is a necessary condition for, okay, let me repeat it. G having no K5 minor and no K33 minor is a necessary condition for it to be planar. And natural question is that would it be also sufficient? And the answer is yes. Wegener in 1937 proved that the graph is planar if and only if it contains K5 or K33 as minor. So this is actually a complete characterization. And indeed, Kratowski in 1930, earlier, actually proved following stronger theorem. A graph is planar if and only if it does not contain K5 or K33 as subdivision. So let me write it. It's K5 subdivision. It does not contain K5 subdivision and all K33 subdivision. As a subgraph. One thing you can easily check is that if you have a graph which is K5 subdivision, it is a K5 minor. In general, if you have H subdivision, it is a H minor. But the converse is not true. There is a H minor which is not H subdivision. It's easy to check. So in that way, I mean, as this direction is obvious, we are really caring about sorry, it does not contain. It does not contain it. So what we actually caring about is that if direction. The other direction is obvious. So if we just consider this direction, then this Kratowski theorem is stronger. It directly implies Wegener theorem. It's not too difficult to actually show that the Wegener theorem also implies Kratowski theorem, so they are equivalent. But anyway, seemingly this one is stronger. So we want to prove this theorem. For that, first we want to define a convenient concept. So we say that a Kratowski subgraph of G is a subgraph of G that is a subdivision of either K5 or K33. So let's define this terminology, which is useful for us. And let's define another terminology for a separating set S of G. What we have S, and then we have some component. And we take each of these or these or these, and then call each G induced by C union S as F log of G for each component C of G minus F. Okay, so we define this terminology. And we want to prove this Grotowski theorem. For that, roughly what we do is we use induction. We consider minimal counterexample. If there is a counterexample, then we choose the minimal one in terms of, edges or, the smallest one. Then we get the non-planar graph where it does not contain K5 subdivision or K33 subdivision. So it does not contain Grotowski subgraph, but it is non-planar. And we want to show that such a thing does not exist. For that, we first want to collect some properties of minimal non-planar graph. So later, we want to consider minimal counterexample. And such a minimal counterexample is non-planar graph, but the minimal one, in some sense. Meaning that if you have a graph and it is not planar, but as soon as you delete an edge, then it is planar. And we want to collect some property of such a graph. For that, let's prove this lemma part, which is convenient for us. If F is the edge set of face in an embedding of G, then G has an embedding where F is the edge set of the unbounded face. So, what does it mean? So you have an embedding of G. You choose any face. Then you can redraw. You can find another embedding of G so that that face, the boundary of that face, is a set of edges. And that becomes the boundary of unbounded face. How do you do it? The idea is that when you have a plane and there is a there is a bijection between a sphere and this plane, except one point. Let's say you have a plane and then there is this origin, 0, 0. You have a plane, R2, and then you consider a sphere which touches at this 0, 0. This is North Pole, and then this is South Pole. And you consider this stereographic projection. From this South Pole, and then you have a point, you draw this line, and that maps this blue point to this blue point. Then obviously this 0, 0 maps to 0, 0, and every point on this sphere maps to plane. That's bijection. So everything except this one point maps to plane. And that's a continuous bijection. And its symbol is also continuous. So, what? Once we have a drawing, once we have an embedding of a graph on this plane, this stereographic projection, so you map this point to here, that gives us an embedding of this graph on this sphere. Okay. And once we have an embedding on this sphere, what we do is we rotate it. We rotate it so that rotate this embedding so that the face that we are considering now contains this south pole. So rotate. And then from this, you again do the stereographic projection. You project back to the plane. And now what happened? This point, the south pole, I mean, the edges or vertices does not cross this south pole. So nothing is mapped to the infinity. I mean, nothing, so every points on this embedding maps to some points on the plane. But what does this become? This becomes unbounded space. So again, you have this embedding, and then you project it to here, and then you rotate so that your desired base F contains the south pole, and then you project it back. Then you can confirm this lemma. So that's the proof. Okay, so this lemma is useful. And then using this lemma, we can prove some interesting property. Every minimal digit property or minimal non-planar graph. Every minimal non-planar graph is two connected. We can show this. How? Let G be a minimal non-planar graph. Then it's easy that this has to be connected. If not, you have a G1 and then G2, which are disjoint component. And by minimality, each of them is planar. Then you draw G1 first somehow. And then you take one face. And then what? You draw G2 on another plane again. And since they are finite graph, you can take a large disk which contains the whole graph, the whole curve and whole point. And then what we do, you shrink this inside of this one face, and then you draw it. Then that gives us a plane embedding of union of these two. So minimal non-planar graph is connected. So maybe I will not write it. And what? Now we want to show that this is two connected. It is connected, we know that. If G has a couple text A, then what? You take a G, you have some components here. And then let's say this is G1, this is G2, this is G3, the lobes. Then let G1, G2, G3 be is P lobes of G. Then by the minimality, G, each Gi is planar. And what do we have? By the previous lemma, each of them are planar. So that means by the previous lemma, we can find the embedding so that the H set of a certain base becomes the base, unbounded base, boundary of unbounded base. Then what does it mean? We can embed each Gi with this specific vertex B on the outside space, unbounded space. Let me know the outside space. Then it's G1, you can draw it somehow, where B is here, and then G2, B is here, G3, B is here, and each of them we can draw, we can embed on the plane. And what? We say fit each embedding to fit in an angle smaller than 2 pi over k at B. Meaning that here, what we fit, we just put, move everything. We just move everything to this way so that it becomes very thin. And again, this, you continuously move everything so that the everything fits into the angle, small angle on here. This again, what? You move everything to here and here so that everything is fitting. You can do that in continuous way. Then, after which, we combine the embedding at B to obtain an embedding of G. Meaning that once we have such a thing, we take a V and then we divide the region into K region. And then you draw G1 here, G1 in one of the region. And G2 and G3, and then GK here. So this shows that if there is a couple text, then it's not minimal planogram. So we just show that how to embed it on the plane. So that proves that every minimal non-planogram is two connected. Okay. Later, when we show the Kuratowski theorem, we want to show that the minimal counterexample must be 3 connected. Why 3 connected is important? As we proved before, in 3 connected graph, you can find the 3 contractor graphs, which will be useful for us later. So for that, we proved the following. Let xy be a separating set of side 2 of G, and let G1, G2, Gk be the xy lobes of G, and let hi be the Gi union with the h. You add an h between x and y. If G is not planar, then some hi is non-planar. So we want to show this. So it's quite similar to the previous one, but this one, essentially what it says is that if a graph is disjoint union, then the entire thing is not planar, then one of them is planar, non-planar. And then here, if you have one vertex which is separating set, and this is S lobe, S lobe, S lobe, And then if G is non-planar, then one of them must be non-planar. That's what it's showing. And essentially, it's the same thing with the costed sides too. But there is additional caveat that here we add an edge between x and y, even if there is no edge between x and y in G. So you will see why this is necessary and why this is useful later. If for HI is planar, then what? Then we embed it. Then by the previous lemma, it embeds with this xy on the outside plate. Then what? We have an embedding of H here. We don't know what it is, but the x and y are on the outside. There could be some more complicated structure here. This is H1, and another is like H2, and so on. And what we have many of these, we can combine such embedding with its successive one embedded in a base of current graph having xy on the boundary. So how do we do it? You draw this inside of this space. Or okay, so for this space and this space, it doesn't really matter. What essentially you can do is that you zoom into here, and then here you have a spacer. What you do is you draw this in a much smaller way. You shrink it, and then you put it here, and then you move this x to here, y to here to like to make sure that this x is actually here and y is actually here. Or you can just imagine moving it to here and then making it a bit big. In either way, I mean, you can either draw this in this space or in this space. It's your choice. And then once you draw it, once you merge two of them, you get the planar embedding of those two, and then you repeat. You have a planar embedding of H1 and H2, so that's a planar. And then now what? Again, you can embed it so that xy is on the outside face. Then you can attach H3 in the same way, H4, H5, H6. Then this gives us the planar embedding. And at the end, now delete xy if it is not in the object. The result is planar embedding object. Here, one of the reasons why we add this xy is that if you don't add xy, then we don't know whether you can embed each gi so that the x and y lies on the same face. There may be no embedding at all, which maps x and y on the boundary of the same face. In that case, I mean, you cannot combine these planar embedding of each gi. So we actually need, in order to get the embedding of G, we actually need the planar embedding of each HI instead of GI. Okay, so now we have collected enough property. We will use this to prove the Kratowski theorem in the next video.